Okay, let's dive into an absolute engineering nightmare. A fascinating paradox where the exact resilience code you meticulously wrote to save your system is actually the weapon that completely destroys it. Welcome to today's Explainer. We are dissecting a failure mode that literally keeps principal engineers and SREs awake at night. We're talking about what happens when well-intentioned retry patterns morph into a massive, self-inflicted denial of service attack against your own infrastructure. If you're a back-end engineer or a system architect, you've probably lived through this, even if at the time it just felt like some unexplainable ghost in the machine hitting you at 2 a.m.
So we have to start with the ultimate production mystery. Just picture this, right? A downstream dependency in your stack degrades for, say, 90 seconds. Your monitoring catches it, the on-call rotation gets paged, but then the dependency recovers. Your dashboards turn bright green, the original fault is completely 100% gone, and yet your platform instantly crashes harder than it did before and stays down for another 40 minutes. You're checking the runbooks, you're grepping the logs, and absolutely nothing makes sense. The system just flat out refuses to come back online even though the backend is perfectly healthy. So, why?
Well, this quote from Rack to Cloud honestly hits the nail on the head. A secondary collapse like that, it's not a new incident. It is your own client logic finishing the job the original fault started. See, teams constantly treat this secondary collapse as a brand new, totally unrelated outage, and they start triaging from scratch. But they shouldn't. It's the original 90-second degradation weaponizing your system's recovery logic to take down the entire platform. All right, here is our roadmap for today's incident autopsy. We're going to cover 1. The hidden retry storm. 2. How traffic multiplies. 3. The recovery cliff. 4. Solutions and safeguards. And finally, 5. Architecture best practices. Let's jump right into part 1, the hidden retry storm. We need to pull back the curtain and look at the actual anatomy of how this self-inflicted DDoS attack forms right under our noses. Think about how a cascading failure actually plays out in production. First, that downstream dependency degrades. Instantly, every single failing client starts a retry timer. Now here's the catch. Those timers are running in parallel, against a wall clock, and they are completely unaware of one another. During the outage itself, the failing service feels zero pressure because it's down. The queue is just growing silently in the dark. Then, capacity is restored, the first health check passes, and boom, that massive, invisible, stacked wave of retries collides with your recovering service all at the exact same time. In simple terms, a retry storm happens when your well-intentioned resilience patterns collide with a temporary hiccup, creating an overwhelming backlog of synchronized requests. You'll sometimes see Azure architecture docs call this a thundering herd. It's totally self-amplifying. The clients fail, they notice the failure, they retry, the system crashes from that huge load, the clients see that failure and their timers fire all over again. The whole cycle just becomes entirely self-sustaining. Moving on to part 2, how traffic multiplies. Where do all these requests actually come from? You might be sitting there thinking, hey, my code only retries 3 times. There's no way that takes down my cluster. Well, let's look at why that assumption is a massive trap. Retries aren't just sitting in your application code. They are compounding across all these uncoordinated architectural layers that literally don't talk to each other. Think about a modern request's journey. You've got hidden vendor defaults in your AWS or Google Cloud Client SDKs. You've got Envoy or Istio's sidecar retry policies buried in YAML files nobody has touched since the platform was built. You have manual try-catch loops written by developers, and then the database layer, which is usually the biggest invisible amplifier of all. The ORM is retrying inside the driver, your connection pool like Hikari CP or PG Bouncer is reconnecting, and then the pool itself retries the reconnect. It's layered chaos. 6. That is the number of hidden retry attempts a single solitary user click can trigger against a failing service before anyone even types a word into the incident Slack channel. 1 click becomes 6 requests. Now multiply that by every active connection in the pool, by every pod in your Kubernetes deployment, by every region in your failover topology. The math gets catastrophic in seconds. Your system's true retry behavior is not the sum of these layers, it's the product of them. So let's look at that math in action. 10,000 clients multiplied by a 5-attempt default SDK policy creates a solid wall of 50,000 requests in a single tick. And let's be clear, we are not talking about 50,000 requests distributed nicely and evenly over a second. We're talking about 50,000 requests hitting your service at the exact same wall clock millisecond. Your infrastructure was simply not sized to handle that. Which brings us to part 3, the recovery cliff. This is the absolute climax of our incident autopsy. The cliff isn't the failure itself. The cliff is the recovery. See, your infrastructure, your connection pools, your autoscaling rules, they're all sized for steady-state variance. They are not sized to absorb the entire client population reconnecting simultaneously. When we design systems, we size them for peak QPS, queries per second. But the capacity metric that actually dictates survival during an incident is peak simultaneous reconnect. And honestly, almost nobody models for that. And this is exactly why autoscaling is not going to save you. The queue builds up silently in the dark and hits way faster than Kubernetes can ever dream of spinning up new pods. While the service is degraded, it's not accepting traffic, right? So the horizontal pod autoscaler sees low CPU usage and does absolutely nothing. It might even scale you down. But the moment that first health check passes and the load balancer reopens the pool, that queued backlog, which could easily be 10 to 20 times your provision ceiling, hits instantly. Autoscaling reacts to sustained load over minutes. A retry storm destroys a service in milliseconds. All right, let's get into part 4, solutions and safeguards. We need to flip to the engineering defense and see how senior architects actually prevent this secondary collapse from happening. First up, pure exponential backoff without jitter is a trap. It just synchronizes your traffic waves. You absolutely have to add decorrelated jitter to smooth out those requests. If thousands of clients fail at exactly T0 and they're all using pure exponential backoff, they're going to retry together at 1 second, then together at 2 seconds, then at 4 seconds. It's like a coordinated attack. By the time 4 seconds rolls around, your service has probably just started to recover, only to get slammed by that entire stacked queue all at once. Decorrelated jitter randomizes that interval within a bounded range, turning a massive synchronized spike into a nice, manageable, smooth distribution. This is literally the highest impact change you can make. Next, we have the circuit breaker. This stops the bleeding right at the source, preventing clients from hammering a service that desperately needs time to recover. Instead of letting every microservice blindly fire retries out into the dark, a circuit breaker detects the sustained failure, trips open, and instantly fails all new requests locally. That gives the degraded downstream dependency the actual wall clock time it needs to breathe and recover, without being subjected to a DDoS attack from its own clients. Then there are token bucket budgets. By using these, you're treating retries as a strictly bounded architectural resource, preventing them from firing indefinitely. Think about it. Most retry policies cap the number of attempts per specific request, but they have absolutely no system-wide budget. A token bucket ensures that if a massive percentage of your overall traffic starts failing, your clients voluntarily stop retrying once that global budget is exhausted. It strictly bounds your worst-case scenario right at the design phase. Now, let's talk about load shedding. The biggest mistake teams make is dropping their load shedding the second the health check turns green. That is exactly when you need it most to survive the recovery cliff. When you are restoring capacity, you are highly vulnerable. If you try to accept the entire backlog at once, you're going right back down the cliff. You have to aggressively reject excess load during that recovery phase, letting traffic trickle in only as fast as your recovering infrastructure can securely handle it. Finally, part 5, architecture best practices. Let's wrap this all up with a concrete checklist of what every production system needs to survive a failure without eating itself alive. You need to walk through your system exactly as a request travels and enforce strict architectural bounds at every single layer. Literally, write down every place a retry can originate, from the SDK to the service mesh to the API gateway, all the way down to the background job queue. Don't let individual teams just write their own custom loops. Use robust abstraction layers like Dapper or libraries like Poly for .NET to make sure Backoff and Jitter are applied uniformly. And hey, if your backend sends a retry after header, make sure your clients actually obey it. That's how you coordinate the reconnect smoothly. Ultimately, remember this. Discipline beats intelligence. You really can't outsmart a retry storm with clever, complex code in just one microservice. It requires rigid, system-wide discipline. Patterns like jitter, circuit breakers, and retry budgets aren't new, but they fail in practice because they're applied unevenly. You might have jitter at the mesh layer, sure, but no retry budgets at the application layer. And the layer without the discipline is exactly where the storm will form. Retry policy has to be a first-class architectural concern, not just an afterthought you slap on. So take a hard look at your architecture today, because I promise you, if you don't own your retry logic, it will eventually own your uptime. The system that recovers cleanly is the one that actively planned for the recovery cliff. Thank you for joining me on this explainer. Go dig into those configurations, check your YAMLs, verify those SDK defaults, and make sure your system fails and recovers gracefully. Catch you next time.